Hey guys, today I'll be giving you a quick overview of Markov chains. Okay, so these are the key concepts that we'll be going over today in our discussion of Markov chains. So if you want to pause the video here, take some notes, these will be the key concepts that we'll be hitting. So to go about our study of Markov chains, basically what we're going to do is we're going to look at a couple of examples. First example reads, suppose in this time of quarantine, Will is either very lazy or very motivated. So on any given day, he either chooses to stay in his pajamas or he dresses formally with suit. So I have this little diagram here kind of depicting the situation. And basically how we interpret this is if Will on any given day starts at pajamas, there's a 70% chance that he will end up at pajamas the next day. And 30% chance that he will switch over to formal. On any given day, if he starts as formal, then there's 60% chance that he'll be formal the next day, 40% chance that he switches over to pajamas. So the question here is, if Will starts by wearing pajamas, what is the probability he is wearing pajamas or formal clothes after 1 day, n days, infinity days? Okay, so we're going to be tackling each steps of this problem using Markov chains. So two quick concepts that we should hit before we start is called the transition matrix and the state vector. So the transition matrix is basically a matrix that we can construct based on this diagram that represents the situation. So how we do that is we name the columns pajama, formal, and basically the columns represent where we start, and this is where we will end up the next day. So if we start on pajamas, there will be 70% chance that we end up at pajamas the next day. If we start at pajamas, 30% chance that we end up at formal the next day, and so on and so forth. That's how we make our transition matrix. Then we'll talk about our state vector, and x sub 0 basically means the state that we will observe at time 0. So the initial state basically, and the rows represent pajamas and formal again, and 1 means we will be starting at pajamas. So this is how we represent that, and 0 means we will not be starting at formal. So this is a state vector, and state vectors can appear at any state. So if we have x sub 1, that'll be after 1 day, and then so on and so forth. So for step A, 1 day, after 1 day. So intuitively, we can kind of see that, according to our graph, if we start at pajamas, then the next day there's 70% chance that we'll end up at pajamas and 30% chance that we'll end up at formal. But what's a more formal way to think about this? Here we'll look at a theorem that will kind of help us. So theorem 10.4.1 says, if P is a transition matrix of a Markov chain and x to the n is a state vector at the nth observation, then x to the n plus 1 equals P times x to the n. This basically means that for a state vector, how we get there is we multiply the transition matrix times the previous state vector. And if we manipulate this a little, this proof, we can also conclude that x to the n, the state vector at nth state, is equal to p times n. So this is what we have here, but it also equals p to the n times the initial state vector, x to 0. Okay, so we'll be using this in our problem. So first one, we want to find after the first day. So we know that it's the transition matrix times the previous day. So what we can do, transition matrix times our initial state. And once we perform this matrix multiplication, we get this matrix right here, which represents that there's 70% chance of pajamas, 30% chance of formal, which is what we expected from up here. All right, so part B, after n days. Okay, so this is where I'll be using the other part of the theorem, so we see that x to the n equals p to the n times the initial state. And we realize a problem here. It's kind of hard to do 2 by 2 matrix multiplications to the power of n. That's like a lot, right? So a trick that we use here is we know that diagonalizable P matrix we can also rewrite as S, D, S negative, X inverse, where D is a diagonalizable matrix, right? So this goes back to some linear algebra that we've learned previously in the semester. So I've done the math here for you. So here are the eigenvalues, eigenvectors, and the SD, S inverse that we got for this problem specifically. Basically, the trick comes here where we realize that P to the n equals S, D to the n, S inverse, times the initial state vector. And these are all now things that we have. And it's a lot easier to raise the power of the diagonalizable matrix to n because this just means we raise the eigenvalues to the power of n. Okay, so we plug these in and we simplify, and this is what we get for n days, this matrix. Okay, so for part C, all we have to do is we take the answer that we got for n days and we take the limit as n approaches infinity. And you notice that when we take the limit as n approaches infinity of 3 over 10 to the n, this becomes 0. So we'll be left with this matrix, and if we multiply this in, we get 4 over 7 and 3 over 7. So over a long period of time, we can end up for the system to end, we can expect for the system to end up with 4 over 7 chance that on any given day, Will is wearing pajamas, and 3 over 7 chance that he is wearing formal clothes. Okay, so this is one way. We'll be looking at some theorems now that will help us kind of shortcut this process and another way to solve like a similar problem. Okay, so some definitions we have here are a regular matrix is a transition matrix where some power of this transition matrix has all positive entries. Okay, so we can see if we look back at our first problem that if we look at all the entries of our transition matrix, we notice that they're all positive. So the matrix we were working with earlier, this does count as a regular matrix. All right, so for regular matrices, there are some special properties that we can observe. So theorem 10.4.2 says that if P is a regular transition matrix, then as n approaches infinity, we get this P to the n equals this, where Qi, so the sum of all the columns basically equals 1. Theorem 10.4.3 is similar. It says if P is a regular transition matrix and X is any probability vector, then as n approaches infinity, P to the n times X gives us this vector, which equals Q, where Q is a fixed probability vector independent of n, all of whose entries are positive. So you might ask, what is Q? Q essentially can also be considered a steady state vector, and this basically represents kind of like the final state of the system, where the system will end up after a long period of time. So whenever a problem asks for, oh, what is the probability of this happening after a long period of time for the system, this is what we'll be looking for, the steady state vector. And our last theorem, 10.4.4, says that the steady state vector Q of all regular transition matrix P is the unique probability vector that satisfies P times Q equals Q. In other words rewritten, this means the homogeneous system I minus P times Q equals 0 has a unique solution vector Q with non-negative entries and the sum equals 1. Okay, so we will be using this to solve our next problem and kind of take a shortcutted process to the similar problem that we just solved. So in this problem, we have that Ben is either happy or sad. If he is happy one day, then he is happy the next day, 4 times out of 5. If he is sad one day, then he is sad the next day, 1 time out of 3. Over the long term, what are the chances that Ben is happy on any given day? Okay, so this is a similar problem to before, but we won't be doing the whole eigenvalue and raising the diagonalizable matrix to the power of n. Instead, we'll be using the theorem that we just learned. So first, we have to check if our transition matrix is regular. And we see that all the entries are positive, which makes it regular, which is what we want. So check. And by the way, the transition matrix, similar to last time, how we got it was if he is happy on one day, then there's 4/5 chance that he's happy the next day, 1/5 chance that he is sad the next day. And if he is sad one day, then there's 2/3 chance that he is happy the next day, and 1/3 chance that he is sad the next day. So that was just a quick review of how to get a transition matrix. So now that we've shown that this transition matrix is regular, we can use the theorem 10.4.4, which says I minus P times Q equals 0. And we need to find Q, this solution, which is what we want, the steady state vector. So we do I minus P, which is what's shown here, times this vector equals 0. And we take the first row here. We get 1/5 Q1 minus 2/3, Q2 equals 0. And we can simplify this to Q1 equals 10 over 3 Q2. Then we also know that because this is part of a steady state vector, these two elements will add up to 1, which is what we've shown here. Then we can make the substitution in here and perform some algebra. And we get Q2 equals 3 over 13, Q1 equals 10 over 13. So we put this into our steady state vector. And this vector basically shows us that over the long term, on any given day, there's 10 over 13 probability that Ben will be happy, and 3 over 13 probability that Ben will be sad on any given day over the long term, which is what we have here. We've answered the question. Over the long term, the chances that Ben is happy on a given day is 10 over 13. So as you can see, this was a similar answer to when we solved for infinity in our first problem. But in the first problem, we basically ran into the problem of having to multiply 2 by 2 matrices over and over again, which is like not reasonable to do. So what we did instead was we found the eigenvalues, eigenvectors, then we rewrote this matrix into the diagonalizable form, and then once we're here, we can raise the eigenvalues to the power of n very easily to get our answer. And that just took a little bit more steps. This one, on the other hand, uses this theorem, and we can just as simply, or much more simply, find the steady state vector, which represents the state of the system after a long time. Well, that's all I have for you guys today. Thank you for watching, and I hope you enjoyed.